the need for conductive spacesuits, a summary of Dream 2 findings.
All right, thanks. Many of the talks you've been hearing so far are inspirational and very strategic. This is just the opposite. This is down and dirty. This is very tactical. This is about walking around in dirt and what's going to happen. And what I'm really going to show is a set of models and simulations of the space environment, space plasma environment, and human interactions therein. And what we're hoping to do is to come up with a survey white paper to pass on to AES. So really based it, so this is really sort of an outline of a report that we're planning on submitting. In general, you might ask yourself, what is a spacesuit? Well, it's a really multitasking outfit. It's a pressure vessel. Successfully completed that work. It's a thermal regulation for the person inside. Provides micrometeoroid protection. There's some elements of the space environment, though, where maybe it doesn't quite do as well, like, for example, protection from radiation, dust adhesion, and in particular, plasma and the electrostatic equilibrium with the environment in the plasma environment. Now, in general, a suit, an astronaut in a suit at the moons of Mars, at asteroids, they're going to be immersed in the space plasma environment, really the solar wind environment. In some sense, they're coupled to the solar electrical system streaming out, originating from the sun, the solar wind, and going out to the outer edge of the heliopause. And there's going to be, for any object, any suit, any part of the suit, there's going to be a set of currents. There are going to be photoelectron currents. This is basically UV light releasing electrons. There are going to be solar wind electron thermal fluxes to the surface, solar wind ion flows, really, it's a directed flow. And then there are secondary electrons. If the electrons coming in are real intense, they can actually kick off secondary electrons. And when you solve for the spacecraft charge, or the spacesuit charge, you actually solve a differential equation. And you assume, basically, the surface will try to get into current balance, and the potential will be such that it'll attempt to balance these currents. What I'll show you also, though, there'll be cases where you're in dynamic, where it's dynamic. In other words, this does not go to zero because you have some kind of fast, quick source that's changing the electrical structure of the surface. So where do you apply these equations? Well, if it's an insulator, and this is important, if it's an insulator, you actually apply these equations locally. So in sunlight, you might have photoelectrons dominating. In the unlit part of the suit, you might have plasma moving in, and as a consequence, you can end up with differential charging. Whereas if you have a conductive body, a conductive suit, really you actually apply these equations globally and come up with one potential, really an isopotential. So why is this a concern? Well, let's talk a few minutes about what we know about spacecraft and their differential charging. It's kind of an analog. And in particular, in the terrestrial magnetosphere, there are actually very, very hot plasma flows in the plasma sheet. And there were reports of charging anomalies when the spacecraft was in eclipse, not in sunlight, and flowing into and you were immersed in one of these very hot plasma flows flowing down the geomagnetic tail. For example, ATS 5 and 6 reported large 10 kilovolt potential anomalies when in eclipse and in this hot plasma sheet. In essence, the temperature of this plasma sheet electrons were about 10 keV, and the spacecraft would charge to sort of large negative values to repel those electrons. Now, to study this effect, in '79, the SCADA spacecraft was launched. They actually had patch plates and found that with different dielectric on them, they could develop differential charge on the order of a few kilovolts. So because of this, it's now common practice for spacecraft to have a skin conductivity requirement, actually really requiring it to be a conductor. So for example, Solar Probe Plus, this is a simulation done by Bob Ergen. And Solar Probe is not a square like this, but he used a square as an example. And looking at the solar wind in closer to the sun, he found the spacecraft would charge up, and you actually end up with these potential anomalies both before and aft of the spacecraft. This one in sunlight from photoelectron emission, and this one in the wake. But the spacecraft surface, because it's a conductor, was basically an isopotential, just a few volts. And this helped eliminate differential charging. So given that we do this for spacecraft, the question is, why don't we have stricter conductivity requirements for spacesuits that are also exposed to this space plasma environment? In fact, for suits, it's even more complicated. If you drew an electrical equivalent circuit for an astronaut, it looks something like this. The astronaut's a capacitor, and as they walk over the regolith, they get tribocharged. So there's a tribocharging source. Now, there's two ways that they can discharge that capacitor. One is to ground, and the other is to the plasma. But as it turns out at the moon, the ground is really a terrible electrical ground in an electrical sense. In fact, the electrical conductivity of a regolith is, in the night side, is about 10 to the minus 17 Siemens per meter. Our ground outside here is about 0.1 to 1 Siemens per meter. So this is about as conductive as paraffin. Actually, it's a little less conductive than paraffin. And on the day side, when it gets a little warmer, it improves a little, but the values, the surface ground is just really a poor ground, especially compared to the plasma. So on the day side, you have photoelectrons and solar wind ions, and they provide a great ground. That's why the astronauts never really reported charging anomalies on their own spacesuits, because they're basically immersed in this conductive environment. But if you get into the night side regions, when you're in the plasma wake, or in shadowed regions where you don't have, like in permanently shadowed craters, you lose your photoelectrons and you have reduced plasma currents. And this could then create increased charging to the astronaut. And it changes your, I just want to mention, it changes your differential equation, because now it's no longer in equilibrium, it's dynamic, and you have a source term, and you also have this ground term. So my colleague Talana Jackson actually modeled this. We have plasma models for particle and cell simulation results, and for the near surface plasma character at the moon. And what she did is she used those simulate environments and stuck them into a charging equation here. And what she found is that when you're immersed in the solar wind, as you can imagine, if you're an astronaut and you're sort of scuffing along every 2 seconds or so, taking a step every 2 seconds, on the day side, no problem. When you're in the solar wind, you may get a little pulse of charge, but you dissipate on time scales of like a millisecond. But if you are in a place where you're no longer well connected to your plasma, like for example, at the anti-solar point or in a polar crater, your source term, your source charging term dominates over the environmental dissipation currents, and you actually can start charging up. So the moral of the story here is, if you're roving, you want to stay in the plasma flow, stay well connected to that electrical ground. We actually tried this at an asteroid. Mike Zimmerman has a tree code, and he actually simulated the plasma environment at an asteroid. Solar wind is coming in from the left. You have photoelectrons from the lit surface, along with a lot of plasma on the day side. So you can think of the front side of this asteroid peanut as being plasma rich, but on the backside, where you're in the wake, you're in a plasma depletion, and you get large potentials back here on the backside. So he passed off his data to Talana, and what Talana did is she put her equivalent circuit model for an astronaut and had him, could be a her too, sort of walk along using the gloves, walking along the surface, starting from the backside here to the front side. And what she found is, as the astronaut walked along the backside, their gloves would charge up. That's, again, because the Tribo Electric source term exceeded the environmental currents back here. But as soon as the astronaut got into sunlight here, photoelectron currents and solar wind, boom, immediately dissipated it, and you're back to zero potential relative to the surface. These potentials are relative to the surface. All right, so let's talk about the suits themselves. Actually, Christopherson and John Lindsay, 2009, John had already passed away, wrote a really nice NASA TM about the Apollo suits. And the big thing about the Apollo suits is the outer skin was woven Teflon, which, honestly, if you had to pick a dust collecting material, woven Teflon is the best dust collector. I mean, first off, Teflon is an insulator, and on the Tribo Electric series, it is one of the most strongly electronegative material you could possibly use. And this material collected dust, both mechanically and through cohesion. The dust stuck in there after the suits returned. So much dust stuck in, John could even do a particle size distribution on what was on the suits. 10 to the 5 grains per centimeter squared along in some of the higher regions, in some of the more dustier regions. So Teflon is just real nasty stuff. Just to show you this, Manisheri and all did a study. They actually put grains in a little mixer and then saw how they charged up. And in that mixer, they could put brass on the outer skin or steel or Teflon. And what you find with Teflon, again, if anything comes in contact with Teflon, it'll tend to charge up positive. Going back to this Tribo Electric series here, Teflon is on the negative side. So anything from the Tribo Electric series that comes in contact with it will charge positive. And sure enough, compared to conductors like steel and brass, the Teflon charged feldspar grains and factor of 10 higher than the conductors. So it's just real, it's a real strong tribocharger. We are now in contact with the folks at Johnson who are doing the Z2 suit, which is the next generation surface garment. It actually is a carbon composite fiber sandwiched in here. And it's really primarily for micrometeoroid impact protection. And we've now shared with them some of our modeling work, and we're initiating some discussions about making this outer skin conductive. So if you had to come up with a set of rules, or we'll call them guidelines in the same spirit as Johnny Depp, if you had to come up with a set of guidelines here, what you really want to do is you want to control tribocharging by not using Teflon especially, but picking something more in the intermediate area of the Tribo Electric series. In fact, if you really wanted to do it, if you knew what the material of the asteroid or you're going to, you actually might want to pick a material in the boot and gloves that has that's very close in work function or Tribo Electric potential to the actual regolith. The other thing you can control is dissipation area, return current collection area. So you want to make your suit conductive to increase A here, and in general you want to stay in denser plasmas. For example, on the day side, 2 minutes, okay. Oh, that's great because I'll talk slower. On the day side of the moon, for example, with photoelectron currents and space plasma, the solar wind, you have about 5 microamps per meter squared generally of environmental current to draw from. When you get into the night side regions, our models and lunar prospector, which is up at 50 to 100 kilometers or so, suggests that these numbers drop by a factor of 10,000 or so. So, and what that does, since the dissipations time goes as 1 over these currents, if you drop the environmental currents by 10,000, that means your dissipation times, your ability to retain charge, is 10,000 times longer. So for best practices for ESD avoidance, you want to it'd be great, ideally you want the human system in sunlight. If you can't have that, at least stay in the denser plasma flow in the solar wind, and really try to shy away from shadowed regions. So to conclusions, key takeaway here, you really want to do everything you can to make this little equation happen here. And that's why you really want a conductive spacesuit to increase your return current collection area for when you tribocharge up. When you talk about roving humans or wheels, you can no longer do what is normally done when people do spacecraft charging, which is to assume current balance. It's actually now a dynamic equation you have to solve. And that's sort of what we've been doing under Dream 2, which is sort of a little different from what people used to do when they did spacecraft charging. Possible ways of remediating this is maybe include an electron emitter. So, you have a source, a tribocharging source. If you also had an emitter, you might be able to also control some of this. And so these are next steps in our modeling efforts, getting more detailed astronaut model. They're more than just capacitor. They're humans. Okay, anyway, so that's it.
Thanks, Bill. Real quick question, if anybody has one. sure you can find Bill after.